咁如果我哋呢個係一個叫做 location 0、location 1啊、location 2。嗱咁咁我哋去寫呢個 Bernoulli equation 嘅時候咧，咁就變咗都係呢個 P1 over 加碼加上 Z1 加上 V1 二次 over 2G 等於 P2 over 加碼加上 Z2 加上 V2 二次 over 2G，OK。嗱咁喺或者我寫上少少。咁嗱 P1 over 加碼加上 Z1 加 V square over 2G 等於 P2 over 加碼加上 Z2 加上 V2 over 2G 佢呢個位咧首先從即係 Bernoulli equation 或者 energy equation 嘅用嘅方法咧，就係、基本上係先列舉咗成條 equation 出嚟，跟住再睇下有冇啲嘢咧係可以簡化或者 cut 咗佢嘅因為 Z1 location 1同埋2咧都係同一個高度嘅，咁所以呢兩個咧係互相 cancel 嘅。咁V1 就未知啦V2 咧就係、一個 zero 嘅，因為佢喺呢個嘅 tube 嘅呢個入口呢個位嘅。咁佢呢度入邊嘅 liquid 咧，咁呢入邊嘅 liquid 咧係靜止嘅，咁所以喺location 2呢個位咧，個 velocity 咧係 zero 嘅即係我哋就係喺個 tube 嘅呢個入口呢個位，個 velocity 咧係 zero 嘅。咁所以咧呢條式咧就剩低咧就係、P1 over 加碼加上 V1 嘅二次 over 2G 等於 P2 over 加碼，即係咁啦。好啦，咁 P1 over 加碼咧就係乜嘢咧？就係呢個就係呢個高度。如果我哋將呢一個高度係假設係細 L 咁樣啦，就係呢個高度。咁而 P2 咧 point 2嘅 pressure 咧就唔係呢度去值咁少啦，佢就係由呢度計算落嚟㗎啦，呢度計算落嚟㗎啦咁如果呢一段咧個高度咧係 L， 跟住上面呢段咧係個 H 嘅話咧，咁呢度就係 L 加上 V1 嘅二次 over 2G 等於H 加上 L 咁因此咧呢個 V1 咧就會係等於咧呢兩個 L 咧 cancel 咗嘅，咁所以 V1 咧就等於根號 2GH 嘅咁就係、如果我哋用一個咁樣嘅 pilot tube 或者叫 pitot tube 去度呢一個嘅向住啲水流去度咧，咁我哋見到佢個 tube 入邊 over 咗呢個 water surface 嘅嗰部分嘅高度咧，就係、代表住佢嘅 velocity head 嘅高度啦咁而個 velocity 咧就可以用根號 2GH 去計算嘅。咁呢個 pilot tube 或者 pitot tube 咧喺現代嘅雖然呢啲係好經典嘅，通過物理嘅方式咧去量度嘅。你會見到咧，即使依家咧即係去到現代咧，除咗呢一啲嘅即係我哋依家好多電子設備啦呢一啲咧就係裝喺飛機度嘅叫 pitot tube 啦咁因為呢 pitot 呢啲物理嘅測量嘅方式咧，佢係非常之可靠嘅因為佢譬如話電子嘅設備機械式嘅設備佢都有可能係某程度上唔知咩時候咧會 fail 噶嘛。咁但係呢啲係唔會噶嘛，因為佢嘅原理咧係擺喺度嘅而嗰個結構咧係非常之簡單咁所以就佢係比較可靠嘅。咁所以咧呢種咧我哋即係通過呢一種方式咧去測量咧佢嘅呢個嘅因為有時候咧你用啲電子嘅儀器去度咧個水標咁樣啦咁你度嗰啲 pressure 或者 velocity 嗰啲 flow rate 你都要 cal 過嗰嚿嘢先準噶嘛
佢呢個例子咧，佢
個速度流動緊。咁你係你係放喺嗰個樓體度噶嘛，係啊。咁咪就係度，其實佢就唔係度緊呢個位嘅速度嘅，佢係度緊佢對前少少嘅呢個位嘅速度嘅，其實嚇。咁所以佢就咁你要睇下你個樓體係咪叫做 uniform 啦。咁如果譬如話你依家係一個 contraction 咁樣嘅，咁你喺呢度度同埋呢度度當然係唔同嘅。咁當然你要去到一個比較 uniform 嘅位啦，即係譬如話一條直嘅批入邊，咁你喺呢度度同埋呢度度咧，基本上就係一樣啦。即係呢個亦都你頭先問嘅問題都係非常好嘅。咁咧就當然你要睇下你要測量嗰個位，你測量嘅目的係想睇乜嘢嘅。咁如果你譬如話你即係需要知道佢一個 uniform 嘅一個嘅 velocity， 咁你就喺一個比較速度比較穩定嘅地方去度咯。咁亦都有啲咧，你有啲地方有啲時候咧，你係想去通過呢啲 tube 咧去度唔同嘅 location 嘅嗰個 velocity 嘅變化嘅，咁咧就會係譬如話喺 wind tunnel 入邊啊，我哋喺 water tunnel 入邊咧，我哋呢啲 tube 咧都會係移上移落去度嘅，因為佢可能唔同離開個 boundary 唔同咧，佢嗰個 velocity 咧有可能係different 嘅嚇。咁另外咧係呢度咧就頭先都有提到兩個嘅 concept 啦，一個叫做 steady 啦，一個係 uniform 啦。大家知唔知呢兩個字嘅喺 fluid 入邊嘅理解係乜嘢咧？乜嘢叫 steady？ 乜嘢叫 uniform 咧？佢係講緊邊方面咧？譬如話 steady flow 係乜嘢意思咧 ？uniform flow 又係咩意思咧？OK 嗱係非常好嗱，呢兩個詞咧都係講緊速度嘅一啲嘅變化嘅。咁 steady 同埋 uniform 係講緊邊方面嘅變化咧？兩個都係個意思都係穩定好均勻咁嘅意思㗎嘛，係咪
？steady 係 over time 佢 distribution。
Yes。
uniform 係喺個 over volume 或者 over 一個 area surface 上去嘅。
係啦，冇錯，非常好啦，呢個詮釋好好嚇。咁咧 steady 咧就係叫穩定啊嘛，咁uniform 咧係均勻啊嘛，係嘛？咁所以 steady 咧佢嘅如果係一個 steady flow 咧，就係用數學語言去表達咧，就 du over dt 咧就等於0。咁即係話係喺時間嘅 dimension 上面咧，個 velocity 咧係穩定嘅即係即係佢唔會，佢呢個咧通常就係睇 local 嘅某一個位、某一個 point 上面嘅咁所以佢係 base on 某一個 point 上面嗰個 velocity 有冇 vary。咁呢個 velocity 咧，因為佢係 vector 嚟嘅咁佢如果個 velocity 有方向或者係有大小嘅變化咧，佢都唔叫做 steady flow 㗎啦，即係 steady 係with respect to time 嘅 ，OK，with respect to time 嘅即係呢個係with respect to time 嘅，咁然後跟住咧uniform 咧就 with respect to location。uniform 係均唔均勻嘅，咁咧就係會睇下佢喺呢個呢個 flow system 入邊係唔係？如果係 uniform flow 咧，佢個 flow 即係喺一個佢嘅呢個 system 入邊咧，個 velocity 咧喺唔同嘅 location 咧，佢係相等嘅咁我哋譬如話，如果一個 steady 嘅 flow，有一種情況係兩種都可以係滿足嘅 steady uniform flow 咁通常如果steady uniform flow 即係話佢既係喺時間上面係穩定，而個地方上面咧佢都係一致嘅。譬如話最簡單嘅，即係譬如話啲 flow 喺直嘅批入面嘅一個流動 咁咧佢呢度流動咧，佢個 velocity 咧係 v1等於 v2嘅嚇。咁呢度呢啲係好常見嘅嚇。咁而有啲時候咧，譬如話佢啲 flow 咧喺一個 expansion 或者 contraction 咧就呢度咧呢度譬如1呢度2咁樣嚇。咁如果佢係咁樣流動咧，嗱因為個 cross section 越細咧，個 velocity 咧係越大嘅嚇。咁喺呢種情況下咧，就係、non-uniform 啦。咁另外一種嘅 non-uniform， 呢種係 uniform 啦。呢種係 uniform 嘅。另外一種 non-uniform 嘅情況咧，就係咧，譬如話佢係一個 rotational 嘅 flow。佢係一種 rotational 嘅 flow， 即係佢好似係一個攪拌嘅情況下，佢個 velocity 嘅 speed 係一樣嘅，個 speed 係 the same 嘅，即係譬如話我哋呢度係 V1，呢個係 location 1，呢個係 location 2咁樣啦linear speed 咧係一樣嘅，但係佢嘅 direction 係變化緊嘅。即係呢啲情況下，呢種都係 non-uniform 嘅，呢種都係 non-uniform 嘅嚇。咁佢喺呢啲即係總之係 non-steady 或者 unsteady 或者係 non-uniform 嘅 flow 咧，佢都會產生一啲嘅 velocity 嚇。即係如果係 unsteady 嘅話咧，呢度就未必可以就簡單地用一張平面圖去解釋嘅嚇。咁譬如話我哋有啲好多嘅例子係乜嘢咧？OK 嗱，呢度咧就係一個啲 simulation 啦嚇，高 quality 嗰啲嚇。咁我哋睇下呢個 simulation咧，佢係 simulate 緊一個叫 Carmen Vortex Street， 係一個比較出名嘅啲渦旋嘅流動嘅。咁我哋是但即係喺呢個 cylinder 後邊咧，我哋睇嗰啲位咧，佢個 velocity 咧係不斷咁樣打轉嘅嚇。見到紅色嘅位咧就係速度快嘅。咁我哋定喺某一個位，喺我呢個 mouse 呢個位，譬如話即係假設啦。你見到佢個 velocity vector 咧係隨住時間咧不斷咁有快有慢有上有下嘅一個變化嘅。咁所以呢度後邊嘅呢個嘅 flow 咧，係每一個 location 咧都係一個 unsteady flow 嘅嚇，即係類似呢啲叫做 unsteady flow。即係如果佢係個 flow 係即係喺時間嘅維度上面咧係有出現一啲嘅唔穩定嘅時候咧，咁佢就叫 unsteady 㗎啦嚇。咁所以大家要知道乜嘢叫 steady flow， 乜嘢叫做 uniform flow 嚇。咁呢啲嘅定義啦嚇，啲 concept。跟住我哋上堂課都回顧咗呢個嘅continuity equation continuity equation 就主要就用嘅比較多嘅就係呢兩條式呢兩條嘅 format 即係呢兩條式嘅話咧，上面嗰條咧5.29呢條咧就係講緊即係一般情況下嘅即係佢有accumulation， 即係話呢個嘅control volume 嘅 mass 有可能會變化嘅時候咧，咁就要用呢條。咁其實就係基本上嘅原理咧，即係個 principle 咧就係你個 control volume 嘅 accumulation 咧就等於加上 outflow 減去 inflow 咧係等於 zero 嘅。咁如果將佢移去等嗰兩邊咧， 就會係個principle 咧，就係 accumulation 咧就等於 inflow 減 outflow 即係一個非常之即係 straightforward 嘅一個嘅 mass conservation 嘅 concept 咁跟住咧，如果係 pipe flow 咧，咁pipe flow 嘅話，因為佢 pipe flow 通常 pipe flow 嘅通常都係啲水咧係充滿晒個 pipe 嘅 area 嘅 volume 㗎啦，咁所以咧入水同埋出水咧係直接相等嘅咁就冇即係除非你係啱啱好開水掣同埋閂水掣嘅嗰啲嘅即係起動嘅嗰下咁如果一般情況下個 flow 係穩定咗嘅話咧，咁佢應該就係出水同入水咧係相一致嘅，即係咁樣咁跟住 conservation of momentum， 咁咧就係就出咗呢個嘅 momentum equation。咁 momentum equation 咧就用嘅方式咧就主要就係呢一種呢一個會用得比較常見啲嘅呢一條式咁而呢度咧，一般情況下我哋去睇嘅啲嘅 flow system 咧都係 stationary 嘅，所以呢一嚿 control volume 入邊嘅 mass momentum change 咧，我哋基本上都係 zero 㗎啦咁主要係睇 outflow 嘅 momentum 減去 inflow 嘅 momentum 係等於翻 add 喺呢個 control volume 嘅 summation force 嘅大小嘅即係一個嘅 momentum 嘅變化。咁呢個亦都係 Newton second law develop 出嚟嘅一條嘅 equation Newton second law 多數係用喺一啲嘅solid 嘅 mechanics 入邊嘅，咁而家呢一條 equation 咧就係用喺啲 fluid 嘅 mechanics 入邊嘅呢條式咧要應用咧就係個要求咧就係你要畫咗呢兩個 diagram 嘅如果需要計算嘅話咁就需要分析個 force 嘅有咩 force 咁跟住咧就係 momentum 啦momentum 就係分析翻有啲咩出入嘅 momentum咁跟住分開就 x y 或者仲有 z direction 去分析翻嗰啲受力就咁啦咁呢條係momentum equation。跟住我哋都係回顧咗呢一個嘅 energy equation 就係呢條嘅呢度啦。咁 energy equation 咧要即係呢個就個玩法上就好多啦就首先就係有啲似係 Bernoulli equation 啦，就係個 fluid 本身嘅 internal 嘅一啲 energy 即係唔叫 internal， 即係佢自己自身嘅一啲嘅 energy。因為如果講認真啲 internal energy 係另外一樣嘢嚟嘅internal energy 係個thermal energy 嚟嘅咁佢個 fluid 嘅本身嘅 mechanical energy， 即係 potential 嘅 energy 加埋呢個嘅 kinetic energy， 再考慮翻咧呢一個嘅 system 可能有 pump 嘅 input 或者有 turbine 去 extract 呢個 energy 出嚟。咁亦都會可能有一啲嘅喺流動過程中咧，有一部分嘅 energy 咧 mechanical energy 咧係轉化咗去 thermal energy 嘅，咁咧就係屬於係 loss energy 咁呢度有 alpha 1、alpha 2咧就一般情況下就 take 1就 OK 㗎啦咁如果題目好特別要求咧，你就通常 assume 係1嘅。處理好多水嘅問題嘅時候咧，我哋基本上係攞1嚟去計數嘅咁head loss 咧，我哋會係後邊嗰個 chapter 咧，我哋會講一啲嘅 head loss 嘅計算嘅 equation。head loss 就有好多種唔同嘅 model 去計算嘅。喺open channel 同埋喺 pipe flow 咧，個 head loss 嘅公式咧都有少少唔同嘅咁跟住如果我哋知道咧係一啲嘅我哋計算一啲嘅泵或者 turbine 嘅 energy 嘅時候咧，我哋就需要用呢條 power equation 咧去 estimate 佢需要幾多泵嘅 power， 或者係會產生幾多 turbine 嘅 power咁呢度咧係會涉及到我哋嚟緊有一個 chapter 咧講緊一啲嘅應用嘅咁我哋會講個泵嘅 system 嘅點樣去 estimate 啲泵嘅。另外咧就係一啲嘅 energy grade line 啦，同埋 hydraulic grade line 嘅 嘅滑嘅方式啦嚇。咁佢哋嘅區別咧就係一個係有 velocity head，一個係冇 velocity head 嘅嚇。咁所以如果當啲 fluid 咧喺條uniform 嘅 pipe 上面入邊流動嘅時候咧，佢哋兩個咧係EGL 同埋 HGL 咧係兩條平行嘅線嚟嘅嚇。咁如果係有泵嘅情況下咧，EGL、HGL 咧就會一齊咧係有 pump energy 嘅 input 咧 ，pump head 嘅 input 咧係 suddenly increase 嘅。咁如果有 turbine 咧就會 suddenly drop 嘅嚇。咁如果有遇到一啲嘅變 pipe 嘅變 diameter 嘅情況咧，咁就會係睇下個 velocity head 咧就會有變化啦，同埋個 slope 嘅 gradient 咧，亦都會因應個 velocity 嘅變化咧，係會係有一啲嘅相應嘅改動嘅嚇。咁如果個 velocity head 越大咧，個 slope 咧就越奇嘅嚇，越 steep 嘅。咁呢啲我哋上一堂課嘅回顧啦 ，OK。So for the main content for this lecture, we start from the topic 2, okay. So for tonight, we are going to talk about the main some contents about the hydraulics, and the first half of this module is about the hydraulics. Hydraulics is mainly talking about the two aspects: the pipe flow and the open channel flow. Alright, so from the topic 2, it is firstly talking about the pipe flow. I think that most of you may have already learned something about the pipe flows ideas, okay, the previous fluid mechanics content. So maybe for the general pipe flows part, I will go a little bit faster, okay. So for the pipe network, okay, well, I will spend more time to talk about the pipe network, how to do the pipe network design principle, and also the how to estimate the pipe network's flow in each pipes in the network. And then firstly, the concept about the laminar flow and the turbulent flow. The laminar, okay, this name is very similar to the worst layer, okay? So that's it is talking about that in the laminar flow, the flow is just like very regular, okay? The flow is like very regular. The flow is not mixed with the other layer. So that for the laminar flow, in this video, the velocity, there is a flow in the transparent tube, and the solid line here, okay, the black line in the middle is actually we call the straight line, which is using the diode to visualize the flow. All right. Now, in the video, the flow of the fluid will increase from the velocity will increase gradually. You can see that what will happen for the line in the middle. Okay. So in the very beginning, the velocity is small, so that the line is very stable. And then when the velocity increase, you can see that in this status that the flow become unstable and appears like the mixing pattern. Okay, become now in the very beginning, we can see that the flow is moving. All right. However, there is very limited mixing pattern for the fluid. So the flow is flowing like layer by layer, and the fluid particle you can consider is very regular. Okay. Now, when the velocity increase, you can see that the diode become unstable. Okay, the straight line become unstable, and this is sometimes we say it is a transitional or the unpredictable flow pattern. Okay, and later we can see that the flow start doing the rotational motion. Actually, it is rotating and moving. Now, just like the volcano vortex stream, okay? Actually, the flow is rotating and moving forward, okay? So that this is rotational flow. And then when the velocity become faster and faster, you can see that the diet become very difficult to identify it is a line, okay? Because it mixes with the transparent fluid very quickly and thoroughly. And when the velocity is fast enough, you can see here, you can, even though cannot see any image about the diet, okay, and the strict line. So this is from this kinds of the situation, it is already in a very fully turbulent situation, okay, fully turbulent situation. So that we can see it again, okay. So the laminar flow to the turbulent flow, okay, it is based on different regime of the flow and very close to the velocity of the fluid. However, velocity is not the main things for the control, because the velocity also need to combine with the viscosity and also the diameter, okay? If only talking about the velocity is not accurate, because sometimes for the water and for honey, okay, if they are running on the same velocity, for example, the water may get into the mixing pattern very quickly because the water has a low viscosity, but the honey has a very high viscosity. If the honey is also running on the same speed of the fluid, they may not appear like the mixing like this, okay? So that for determine the laminar and the turbulent flow, it is not just considering the velocity, but we will use, okay, now here in this figure also talking about the same thing. For the figure A, for the part A, it is the laminar flow. It is clearly see at the line, okay. For the figure B and should be figure C and D, it appears like the mixing and the sometimes the rotational flow pattern, okay. Now, to classify the flow in the laminar region or the turbulent region, we will use the famous non-dimensional term, or we can sometimes say it's a pi group. Okay, a pi group. A pi group is a dimensionless group. Dimensionless. Okay, the pi group is also named as a dimensionless group. Now we can see that in the modeling, we use quite often that using the dimensionless group for finding the relationship between the parameters. Okay, this is based on the dimensional analysis. We try to use the dimensionless group to minimize that the relationships. Okay. Now the Reynolds number. Okay, the Reynolds number. It is RED. RE subscribe D. Okay. The Reynolds number is not only used for the pipes. Okay, it can be used for many scenarios that related to the fluid. So that the Reynolds number is mainly, there are four mainly calculation equation. VD over nu, okay, VD over nu, or rho VD over mu, okay. We mainly use these two. Now, V is the velocity, very clear, okay. Now, V is the velocity, D is the diameter, okay. I think this is very clear. Now, this is something very similar to V, but it's a squid symbol. It's new, okay? This is new, it's not V. I'm not sure that whether some of you play Gundam model before. High new Gundam, okay? Do you know what is the 海牛高達？有冇聽過 ？High new 高達就係呢個啦。Okay, this is new. This is new. Okay, pronounced as new. So it is a Greek symbol. It is in yes, both this mu. Okay, this mu. Both are viscosity, but this is a kinematic viscosity. This is a dynamic viscosity. What's the difference? Their relationship is the nu is equal to the mu divided by the rho. Rho is the density, you know. Okay, their relationship is like this. The viscosity will affect that the viscosity. Now, the kinematic viscosity, the unit is usually the meter square per second in the SI unit. The dynamic viscosity is Newton second per square meter, or sometimes the simply the Pascal second. Pascal second. Okay. Now, for a very easy remember value is that the mu of water in 20 degrees Celsius is equal to 10 power minus 3 ns per meter square, and the nu for water also at 20 degrees Celsius is 10 power minus 6 meter square per second. So, in this equation, the Reynolds number is calculating the Vd over nu, or rho Vd over mu. They actually talking about the same calculation. Now sometimes if you don't use the velocity, you may use a Q to replace the velocity for this calculation. So there are four calculation equation for the Reynolds number, but most of the time we use the first two. Okay, use the first two. Now the viscosity affects that we say the flowability of the fluid. If the viscosity is high, that means that the fluid is very difficult to flow, okay? Or the resistance is high when it's flowing. Now, in the fluid mechanics, we have introduced that the Newtonian fluid, okay, and the non-Newtonian fluid. Now, Newtonian fluid is talking about that if the fluid follows that in this figure, okay. Now, if there is an equation, we say the Newton's laws of viscosity, but it's not the main thing here, okay. Newton's laws of viscosity, nu is equal. Shear stress is supposed to be a shear stress is equal to nu times d velocity over dy. Okay, Newton's laws of viscosity. This is talking about the shear stress for the flowing fluid. Okay. Now, if fluid follows that Newton's law of viscosity, that means du over dy and the shear stress is on a linear relationship, the straight line. We call this is a Newtonian fluid. If it is not linear, it is non-Newtonian fluid, the other ones, okay? There may be the latent fluid or pseudoplastic fluid or plastic fluid, okay? Or sometimes we say this is a shear thinning and this shear thickening, and this is the Bingham plastic fluid, okay? Now some of the example can be like in this video, just for information for this part, okay? It's not for the main content. It's interesting. Now we can usually understand that the low viscosity fluid is mainly the Newtonian fluid. For example, water, the oil, the honey in not a very high concentration situation. The air are supposed to be most of the common fluid that in our daily life is the Newtonian fluid. Okay, some of the now this is the liquid honey, but the viscosity, the concentration is not that high. Okay, so that is like it's not flow like the water. Okay, so that but if the honey is in a very high concentration, it will become a shear thinning. Okay, shear thinning, just like a toothpaste. Okay, 好似牙膏嗰啲都係類似係呢啲嘅 non-Newtonian fluid。佢 non-Newtonian fluid 呢個 shear thinning fluid 咧，佢嘅特徵咧就係咧，你要即係譬如話你要將呢個 honey 倒出嚟咧。你同倒一杯水係唔同嘅，你係需要咧係將佢傾斜得多啲嘅，即係話要俾一個大啲嘅 shear force 佢咧，佢先至會 flow 好似啲液體咁樣 flow 嘅。如果你嘅俾嘅 shear force 咧唔夠大咧，佢就未必係個 flow 咧未必咁即係個流動性未必咁好嘅。OK。另外一種咧non-Newtonian fluid 咧就類似呢啲嘅好結塔嘅咁樣嘅一啲嘅，佢其實就唔係一種又唔係一種溶液，就好多時候係一種嘅類似嗰啲膠體狀嘅嘢嚇，即係我哋常見嘅。如果喺工地咧，你都好常見嘅一啲嘅石膏嘅嚇，石膏嘅水同埋石膏嘅混合物咧，佢係屬於係一個 non-Newtonian fluid。其實英泥都係，即係如果係啲即係未乾嘅石屎啦嚇，即係都係屬於係 non-Newtonian fluid 嘅 shear thickening 呢個 shear thickening， 佢嘅特點咧就係你用一個比較細嘅 shear stress 嘅喐佢嘅時候咧，佢會係流動性係比較似係 fluid 嘅，但係當你如果用一個比較大嘅 shear stress 去衝擊佢嘅時候咧，佢反而咧就會冇咗個流動性嘅，因為佢嘅分子嘅分佈咧，當接受緊大嘅衝擊力嘅時候咧，佢嘅反作用力咧係相對比較大嘅，即係好似咁樣嚇。咁呢種係另外一種嘅non-Newtonian fluid 嚇。咁呢度 for 大家 information。So because the viscosity is also used for the calculation in the following content, so I just would like to refresh you some memory about the viscosity. Okay. Now, but because viscosity we can find in some handbooks or in some figures or diagram, but most of the time in this module I would directly tell you. Okay, for this for the fluid in certain temperature. Okay. Now, the Reynolds number is a number, so this has no unit, okay, because it's a dimensionless group. So if the Reynolds number is smaller than 2000, it is classified as the laminar flow. This is talking about in pipe flow, okay, in pipe flow. RED is mentioned in the pipe flow, okay. Now, in the open channel flow, the number is not like using the 2000, okay? Or in the groundwater, it's not using 2000. This number, this value to determine the laminar flow and the turbulent flow is talking about in the pipe flow, okay? In the pipe flow. Now, developing flow and developed flow is just for information as well, okay? Because sometimes when the fluid flows from one section to another section, there must be a distance that the fluid's velocity profile is changing from one to another, okay? Now, for example, if the fluid flowing from a tank to a pipe, okay, initially the velocity entering this entrance, it is very uniform distribution. However, because of the boundary layer, okay, because of the boundary layer or the friction from the boundary, so that the velocity will start to develop a very significant boundary layer and making that. All right, here we need to talk about a concept. It is the no slip condition. 大家知唔知咩叫 no slip condition 啊？對呢個名有冇啲咩印象啊？嚇 ？boundary layer effect，OK， 係嘅boundary layer 嘅話咧，就係喺呢個 boundary layer 呢個位咧，佢係好得意喎，即係個 fluid 喺個 solid boundary 呢度咧，佢嘅 velocity 咧係等於0嘅，即係話係 just at 呢個 boundary layer 呢個位咧，佢係冇 velocity 嘅，個 velocity 等於0嘅。嗱，咁 no slip condition 咧可以通過呢一個video 咧去驗證嘅。嗱，咁呢度係呢張呢個 video 咧就係黃色嘅地方咧就係喺一個 channel 入邊嘅，咁咧啲水咧就係由呢個右手邊咧流去左手邊嘅，係一個咁樣嘅流動方向嘅。咁呢一支黑色嘅呢一支針咧，佢就係 inject 一啲 dye 咁咧佢依家咧係黐住，即係懟到落去個 channel 嘅底部嘅，去 inject 呢個 dye 嘅。大家留意下咧，咁佢 inject 呢個 dye 咧，咁佢依家離開咗啦就佢一部分嘅 dye 咧就係喺呢度 inject 嘅，咁另外一部分嘅 dye 咧就係隨水漂流嘅佢離開過呢個底部嘅，咁離開呢個底部咧，咁佢會喺呢度咧，咁兩種嘅唔同嘅狀態啦，咁隨住呢個時間推移啦，咁佢離開個缸底嘅呢個部分嘅 dye 咧，佢係隨住呢個嘅液體咧係流動嘅，但係喺底部咧，你見到佢個流動咧係有一部分嘅 dye 嘅 particle 咧。係基本上係黐住咗喺底部嘅，佢基本上係冇喐嘅。佢而呢個 dye 咧並不是係held 咗喺上面，即係唔係好似油漆咁樣係黐實咗，即係唔係化學嘅作用咧黐咗喺度。佢只不過係呢個 particle 咧喺個底嗰度咧係冇 velocity， 所以佢就好似 settle 喺度咁樣啦，settle 喺度嘅。咁點驗證佢係 settle 喺度定係黐咗喺度咧咁佢等間咧會用一支羹咧去搞佢嘅咁佢咧搞佢之後咧，佢就走咗啦咁即係話啲 particle 咧並不是係好似啲即係油污咁樣黐咗喺度，佢只不過係 settle 咗喺個底部。點解會 settle 咧？係因為個底嗰度咧個 velocity 咧係等於0嘅。咁呢個就係所謂嘅 boundary 所謂嘅 low slip condition low slip condition 係講緊咧，就話喺呢個 flowing fluid 嘅時候咧，佢嘅 boundary 咧個 velocity 咧係等於 zero 嘅，即係個 boundary 即係 solid boundary 嗰個位咧個 velocity 咧係等於 zero 嘅。 咁咩叫 boundary layer 咧？我哋亦都睇一個 video 咧，去睇翻呢個 boundary layer 係咩嚟嘅。嗱，我哋睇下啦，就我哋睇到咧呢個可能。咁呢個係一塊好薄嘅 plate 啦嚇，咁跟住咧佢呢度 jam 一啲嘅 hydrogen bubble， 咁咧你見到咧喺呢個前端咧佢會界開咗呢一紮嘅hydrogen bubble 嘅，即係白色嘅嗰啲嘢嘅，咁咧就會係當佢喺呢個plate 嘅呢個表面嘅時候咧 velocity 係零，咁但係呢啲 bubble 係喐緊噶嘛，咁所以佢一定係會有一個嘅區域咧係由零嘅 velocity develop 去一個佢依家嘅喐緊嘅uniform 嘅 velocity， 大家望下咁就係會形成咗呢一個少少好細好薄嘅一個 layer 咁呢個 layer 咧個 velocity 你見到佢呢度咧係零，因為零 velocity， 所以佢呢度咧係如果 hydrogen bubble 係喐緊嘅話咧。同一時間喐嘅話咧，佢呢度咧就會係應該呢度係會見到白色嘅，咁但係底下呢度冇嘅，咁即係話呢個位咧就係冇 hydrogen bubble 喐過嚟嘅，咁但係呢啲 hydrogen bubble 係喐緊啊嘛，咁所以咧佢會係拉扯住咧有一個呢一個 boundary layer 度咧就係由零嘅 velocity develop 到去佢某個速度嘅 velocity 啦咁所以呢個就係個 boundary layer， 咁而呢度咧亦都睇到個 low speed condition 嘅情況嘅咁個 boundary layer 咧，雖然佢係一個好薄嘅一浸，但係佢係形成咗呢一個嘅head loss 嘅一個最主要嘅地方即係形成咗呢個 velocity 同埋 energy loss 嘅一個最主要嘅地方佢之後咧有個係隨住佢嘅變化啦。咁呢度嘅呢個 video 咧就睇到咧個 boundary layer 咧會變得越嚟越厚嘅，但係又唔會無限咁厚嘅 ，OK？ 即係佢會係沿住呢個嘅 plate 嘅一個前端位咧，佢 develop 落去咧就係一個越嚟越變厚嘅一個嘅情況嘅。大家再睇多次。佢會係由薄嘅跟住慢慢變厚嘅呢個 boundary layer咁係因為佢去到後邊咧，佢呢個嘅原因係因為佢產生咗一個 friction， 呢個係一個 stable 嘅，即係叫 stationary 嘅 plate， 跟住喐動緊嗰啲白色 bubble 咧，佢係屬於係嗰啲有 velocity 嘅咁佢個 boundary layer 咧會越嚟越厚嘅咁但係又唔會無限咁厚到一定程度咧，佢就會係比較 stable 噶啦因為佢形成咗個平衡形成咗平衡。So when we come back to this figure, so that it is when the fluid flowing from a tank to a pipe, actually they forms the boundary layer, okay, boundary layer. So the boundary layer become thicker and thicker, and so that making that velocity changing from 0 to a certain value, okay. So that finally the flow will become very stable velocity distribution. We say that in this region is a fully developed flow, and this region is developing flow. Okay. Now, why do we need to know this small area and the distance? Now, usually, sometimes you are asked. Now here is the estimation of the entrance length distance, okay, entrance length. How long will this developing flow develop? Now this is sometimes used for your consideration if you are asked, okay, to install a meter to measure the flow or measure the pressure, okay. If you are installing the meter in this region, okay, the flow may be unstable, okay? The flow may be unstable. So that's sometimes that this velocity profile may not be very representative, okay? So that you may consider to install the meter, for example, the flow meter, in this developed flow region, okay? This is more preferred. so that this will make your measurement of the velocity or the flow will be more stable and more the data will be more stable and more useful. Okay, so this is the now when you are going to buy a measuring device, for example, pressure meter, the flow meter. Usually, it will ask you. Okay, it will ask you that install. For example, if you have a pipe section, okay, to install the meter, okay, sometimes we buy the flow meter. They will ask that you may need to have 10D distance away from the previous transition, and maybe 5D, okay, 10D and 5D away from the next transition, okay, to make sure that this flow measurement is stable, okay. 10D and 5D, it means that the D is the diameter, okay, so that it will help you to find a better location to have a more accurate measurement of the flow, okay. So this is the what the entrance length is used. Now next is talking about some introduction about the pipe size, okay, the pipe size. Sometimes when you have done some calculation of the necessary diameter, however, it is not able to exactly ask the manufacturer to manufacture or produce a pipe size that according to your necessary diameter. So that's sometimes you need to refer to some commercialized product, okay, from the supplier. So usually you may use the DN pipes to do the to buy this kinds of material for the design, okay. Now the DN is kinds of the standard diameter in most of the countries, okay. So it controls the outer diameter mainly, okay. It controls the outer diameter, so that the DN pipes, the outer diameter must be the same or very tiny variance. However, due to different schedule or the wall thickness, the inner diameter may vary, okay. So that when in your calculation, the inner diameter is the thing that you calculate. However, okay, you may need to determine what kinds of the wall thickness of the pipe you are going to use, so that you will, when you have done, for example, you have done the necessary diameter of 20, the necessary diameter D in the calculation is 200 mm, okay, it's necessary. Now, actually, the 200 mm is very likely the DN200 pipe. Now, but the DN200 pipe may, according to the manufacturer's manual or the catalog, all right, there may be the 40 schedule or 80 schedule for different wall thickness, okay? Different wall thickness will result in different inner diameter. So that sometimes if the inner diameter is less than 200, most of the time you will consider to use the larger size. For example, DN205, 250, okay, to fulfill that your necessary diameters requirement. And then you will use, if you think that the 202.7, this one is the one you select, you may use the 202.7 to do the calculation again for the head loss and other flows, velocity, to see what are the what if you use this kind, you have select this pipe to in your system, okay? So so this kinds of calculation you need to refer to the manufacturer's catalog, okay? Now, next is talking about the head loss in the pipe system. The head loss in the pipe system. The head loss is a very essential things that in our design or the calculation, okay? Because you see that in the energy equation, we pay attention to the flow energy and the energy input, for example, the pump and the turbine, and focus on the head loss. Okay, the head loss will determine that whether you need to use a pump or whether you how much turbine energy you can extract. Okay, the pipe flow's head loss is mainly contributed by the two aspects. One is the pipe head loss. Okay, the frictional head loss comes from the friction of the wall material. Okay, usually the wall friction. The component head loss comes from the fitting. Okay, comes from the fittings. For example, the valve, the bands, and the teeth. Okay, these types of the fittings in the pipe system. Some textbook may call this is the major head loss. Some textbook may call the component head loss is minor head loss. Okay. One is the major loss and the other one is minor loss, because sometimes, in most of the time in the pipe system, you may have very loss of the straight pipe, but less amount of the bands or the joints of the valve. And usually, okay, the component head loss is sometimes less significant than the pipe head loss. Okay. So for different textbook may have different name. Mainly contributed by these two. Okay, for a pipe system, you may need to calculate pipe head loss and the component head loss and add together. Okay, to estimate the total head loss. Now here is the next content is talking about how to work out the equation for the frictional head loss calculation. Now, there are three models that use quite popular, okay, in the head loss calculation. Now, one is the Darcy-Weisbach equation. Darcy-Weisbach equation has Darcy friction factor, the f, the small f. The small f is also a dimensionless factor, dimensionless slope. It's 4 times the tau 0. Tau 0 is the wall shear stress. Wall shear stress. Okay, wall shear stress. The shear stress is linearly distribution. Okay, it's linearly distribution. The shear stress at the, or we may say it is like this. Okay, the shear stress at wall is the maximum. At the center, the shear stress is equal to 0. Okay, at the center, at the center line, the shear stress is 0. Okay. Now, so the frictional factor is 4 times the wall shear stress over the kinetic pressure, rho v squared over 2. Yeah. Now, but most likely, most of the time, we are not going to calculate in this way, but we will use a Woody diagram to look for the value for the frictional factor. Okay. Now, by the use of the frictional factor, we have the first popular equation in the calculation of the head loss is the Darcy-Weisbach equation. Similarly, we sometimes in some model we say the DW equation. Okay, the DW equation, the Darcy-Weisbach equation. Now, this equation is I think that this equation is it's not so complicated. Okay, it's the frictional factor F. L is the length of the pipe. D is diameter. V is the velocity. Okay, F is the friction factor. So the F is the Darcy friction factor. Okay. Now this head loss equation, Darcy friction equation, Darcy-Weisbach equation, can be sometimes modified to this format, okay, KQ squared. Well, how to do this change? But this form will be used in the pi network system calculation. Now this is because that because in the pi network system we sometimes focus on the Q, the discharge. The velocity is equal to the discharge over the area of the pipe. If it's a round pipe, it's equal to pi over 4 times d squared, right? And if we combine these two equations, the HL, the head loss, is equal to the FL over D, Q over pi over 4d squared and square and over 2g. Now, after rearrangement, it will be equal to the 8FL over pi squared GD power 5Q squared, okay? So, it's using big K to represent this the calculation, this group of calculation. Some textbook may use ALO, okay? Some textbook may use ALO to stand for the group of calculation. Now, because in the pi network, okay, in the pi network, it is this kind of a K factor is not changed very significant, okay? So that the change of the flow is mainly due to the head loss may be mainly affected by the Q, okay, discharge. So that this K factor is usually very stable. So it sometimes use this form, the KQ power n form, to represent the head loss, okay? Now this is the Darcy-Weisbach equation. Darcy-Weisbach equation. In this module, I think that I'm not spending so much time on talking about how this equation is developed, but I have this part of content. If you want to know more about how this equation is developed, you can study by yourself. We may be talking about how to use this equation to do the calculations later, okay? Now, another model for the head loss calculation is the Hazen-Williams equation. Hazen-Williams equation, okay? Sometimes it's also WH model, WH equation. This equation seems that the equation is not it's very empirical format, okay? Because the power form is not an integer number. It's 0.63, 0.54, this kinds of the factor. KH is unit conversion factor, okay? Unit conversion factor. C is the Hazen-Williams roughness. Here it has talked about that. C is the Hazen-Williams roughness coefficient. R is the hydraulic radius. SF is the friction slope. This equation is not directly for the calculation of, this is calculated velocity, okay, to estimate the velocity. But this equation is for the Hazen-Williams equation head loss term. It is per 1,000 feet or 1,000 meter. Okay, depends on the the unit you use. Okay, there is also a unit conversion factor, which is there is two format. Okay, A Q over C power 1.85, D power negative 4.87, or BQ C over C D power 2.63 power 1.85. These two equations, okay, this is putting the A outside the bracket and D outside bracket, but this one is putting the A becomes a B into the bracket and D become into the bracket, okay, so that there are two formats. The A for the SI unit is 10,070. B is 1,400. B is 151 for SI unit. For the US unit, the B is 149. For US unit is 10,500 for US customer unit. Okay. Now C here is still the Hazen-William equations coefficient roughness, or we say the WH roughness. D is diameter for sure. Okay. Now for this Hazen-William HW, sorry, not WH, it's HW. Hazen-William equation roughness. You can find this information from this table. According to different pipes condition and the new pipe or the old pipe, okay, the Hazen-William coefficient considers that the age of the pipe, and then this equation, this figure, the table, also lists out the Manning friction factor, Manning's roughness, the Hazen-Williams roughness, okay, and the KS. The KS is the surface equivalent roughness height for the Moody diagram, or for the Darcy-Weisbach equation. Okay, the three roughness comparison for different pipe material. For ductile iron, okay, ductile iron is a very common water supply pipe that used for the main pipe. Okay, in nowadays, some of these are coated by the asbestos, okay, cement, or some of the casted by the epoxy, and see that whether there is any epoxy lining. Seems no, okay. Nowadays, sometimes we coat the ductile iron with the epoxy, so okay, so you may need to look for some international information, okay. Now, next is now the Hazen-William equation also can be converted into the KQ power n's format. Because the discharge here is power 1.85, so that in using the Hazen-William equation, the KQ is power 1.85. The K is calculated like this. This phi is also the unit conversion factor for US unit and SI unit. Okay, L is the length of the pipe. Okay, in the feet in the US unit, and the meter in the SI unit. Okay. The third model for the head loss estimation is the Manning equation. Manning equation usually we will use in the open channel flow or the drainage pipe. Okay. The Manning equation's head loss calculation is, since that the model is very complicated, okay, is n square L over beta R power 4/3 and A square and Q square. Okay, N is the Manning friction factor. Manning roughness factor. R is the hydraulic radius. Beta is the unit conversion factor, okay? Beta is unit conversion factor. A is the area. A is the cross-section area. So in US customary unit, usually it is feet or this unit, okay? In the SI unit, it's usually meter, okay? Now, so that the Manning's roughness is also can be found in this table. Can be also found in this table, okay? Now we will have some. Okay, so here we have introduced the three models for the estimation of the head loss. Okay, the Darcy-Weisbach equation, the Hazen-Williams equation, the Manning equation. Three models. Okay, three equations for estimating the head loss. So later we will have some examples or tutorial question to show you that what's the difference to use these three equations to estimate the head loss. Okay. Now at this moment, we may take a 10 minutes break, and then we will come back at the 8:40 p.m. to continue the remaining content.